So we considered Hermitian vector bundles, and we defined some tensor fields on a complex manifold associated to a Hermitian metric. So we have a complex manifold with a complex structure I. And we have a Hermitian metric on M. So which satisfies all those properties I mentioned last time. And then we have two things. So from here we obtain a Riemannian metric. Hello. And we also have a two-form. Well, it's a real two-form actually of type 1,1 in fact. A real two-form of type 1,1. So briefly, it was defined that H. Well, it was defined using the following identity. For the two tangent vector fields U and V. And so we said that this metric H, or the metric G equivalently, is that it is scalar if this form omega is closed. We also have seen some properties. So the main thing to remember is that this G is invariant with respect to the action of the complex structure, and similarly for omega. And they are related in the following way. So one can reconstruct one of them from the other via the relation like this. So H or G is scalar if, so this G is scalar if the two form is closed. And we've essentially seen, so there was also this this local expression which is sometimes useful. So locally we may write this like this. So it's a sum of hij dz I which dz j bar, and these are functions defined as follows. So there was like this, and also there was an example of this Keller form on a projective space. It was called Wvedienie metric on CPN. This was defined as the unique UN plus 1 invariant, well, unique up to a multiplication by a constant, UN plus 1 invariant Hermitian metric on CPN. Well, I mean, it is unique in the sense that if we fix the Hermitian structure on the vector space, so this is a projectivization of n plus 1 dimensional vector space, and if we fix a Hermitian structure on this vector space, then we have this unitary group. It also acts on CPN, and then the metric is uniquely associated to this action. So the unique U n plus 1 invariant Hermitian metric yeah. And we have seen that it is automatically kähler. So sometimes it is also useful to have this local expression, and there is an exercise in the new exercise sheet. So there is actually the new exercise sheet. So one can write down the formula for this Fubini-Studi metric. So this is Fubini-Studi. This will be imaginary unit del bar of the logarithm of the following expression. So these x, I, x, x1, xn, these are coordinates on Cn. That's one form, so you can check that it's positive. And so this Cn is, we view it as an affine open subset in CPN. But so you can cover CPN with such affine subsets, as I have explained already in the first lecture. And then you may check that these forms in those local affine charts, they glue together to produce a Hermitian kähler metric on CPN, and that is the same metric. So you can think why it's the same metric. That's an exercise. All right. So then, so how to construct more examples? Of course.
Это же плохая метрика в Губкине, да, если не хватает двух пей знаменать. Ну, значит, что это, это не образующая вторых коммун.
Да, наверное, сейчас сказать, ну хорошо, да, я как-то не задумывался о том, как отнормировать ее так, чтобы она была злочисленной.
На 2 пи разделить.
На 2 пи разделить, да? Ну, хорошо. Спасибо. Okay, so if we divide by 2 pi, then we should get actually the cohomology class of this form will be integral. Yeah, I suppose I haven't checked this, but yeah, I believe you're right. And so more examples, how to construct more examples. So first, if we have a complex submanifold inside a kähler manifold, then we can restrict our 2 form to n. So n is a complex submanifold. Спасибо. So assume that omega is the kähler form on M. then let's restrict it to n. So let's write omega n just for the restriction. And then I claim that this is a Kähler form on n. So what do we have to check? Actually, so there are two conditions. So first, that it is invariant and positive definite, and that it is closed. So it is closed obviously because it's a restriction of a closed form. So d omega n is of course the same thing as the restriction of d omega, which is 0. And the other conditions are also obvious because the tangent space to n is preserved by this complex structure. So when we look at these conditions, we just have to take some tangent vectors to n, apply the complex structure to them, and check this invariance and positivity. But since they are satisfied on m, they will be also satisfied on n. So this will be invariant and positive. So that's a Kähler form. In particular, all projective varieties, they are closed complex submanifolds in CPN, they are Kähler. Okay, so yeah, so here the conclusion is that so omega n is a Kähler form on M. In particular, all projective varieties or projective manifolds, because we don't want to assume that they are, we want to assume that they are smooth, so all projective manifolds are Kähler. Okay. So then there were several other constructions of complex manifolds, and under most of those constructions, the property of being Kähler is preserved. So, for example, if M is Kähler and we take some covering, well, a covering, or you may say a local isomorphism, for example, so it does not have to be a covering, a local isomorphism. This means that every point in M tilde has a neighborhood which maps isomorphically to an open subset in M. And then, of course, we can pull back a Kähler metric on M, and this will be Kähler on M tilde, because this condition of being Kähler can be checked locally, clearly. So this invariance is a local condition, so it's enough to check on an open covering, and then that the form is closed as well. So this will be Kähler if this is Kähler on M tilde, if omega is Kähler on M. Also, we can take quotients if we have some group action, and we have some Kähler form that is preserved by this group action. A G invariant Kähler form. Well, we should also assume, as before, the first lecture, that this quotient is well defined, so that the action is, has some good properties. For example, it is free and properly discontinuous. So assume G acts freely and properly discontinuous. So that the quotient exists, and there is this map to the quotient, and it's also a local isomorphism actually. But now we want to push forward the matrix. So before it was a local isomorphism, we pulled something back, but here we want to push forward. So how to push forward? The push forward of a differential form is not well defined, but actually we just take some point in this manifold. We take a neighborhood of this point. So that's a point in M, X, and that's its image under the quotient map. And then there is a neighborhood of X in M that maps isomorphically via pi to an open neighborhood of this X in square brackets. And so we can let's call this V, and then define just omega V to be somehow let's say so pi I mean I identify this V with U, and then I just restrict, so let me just not make the notation too complicated. So that's just the restriction of omega to this open set in M, and I identify it with an open subset of M mod G. And then I claim that all such omega V's for different open subsets V, so they all glue together to a Kähler form, just because if we have for different open subsets V1 and V2 as above, these two we have these two preimages of these open subsets in M, and on the overlap somehow we go from one preimage to the other by the G action. And so we have, for example, here it is U1 and U2 in M. So we may choose those preimages to be such that the intersection of V1 and V2 is just isomorphic to U1 intersected with U2, but then somehow so the definition of this omega V does not actually depend. Okay, so let me erase this. I want to say that omega V1 restricted to the intersection coincides with omega V2 restricted to the intersection because of the condition of G invariance. So for all elements of the group G, we have the property that the pullback of omega is omega. So somehow if we have these two open subsets in M, So I get from one of them to the other by the g action. So this is somehow, so the two of them, they map to the quotient, and here in the quotient they already intersect, but here they may not intersect, but then I can apply g action, and then somehow when I go from one to the other by the g action, then the form does not change, so the corresponding forms on v1 and v2, so they coincide. Okay, so is it clear? I see. Okay, so then let's go on. Yeah, well, of course, the main example here is a complex torus. So a complex torus is the quotient of Cn by some lattice, so lambda, which is isomorphic to Z2n with a lattice in Cn, and I take the standard flat Hermitian metric on Cn. It is lambda invariant. So I mean lambda acts on Cn by translations. Obviously this form is invariant under translations. And so it descends to the torus. So the torus is a Kähler manifold. Also there was an example of a blow up. So we had an example when we blew up a point in C2, and more generally I mentioned that one can blow up a manifold M along some submanifold N of a blow up of M in a submanifold N, and this blow up will be Kähler if M was Kähler. But I don't want to give a proof. You can think about it, so it's not obvious actually at all, because if we take the preimage of the Kähler form on M, then it's not, it is a 1-1 form, but it is not always positive definite. So this blow up, it contracts a device in M tilde, the form will not be positive along the directions that are contracted. But nevertheless, you can still prove that M tilde will be Kähler, but the proof is a bit technical. So I decided I just don't want to, because we will not really, talk too much about blow-ups. I don't want to show you the proof. So, okay, what's wrong? Okay.
So maybe you can present. So idea is to glue the original Keller form on M and Keller form on CPN or something.
Yes, it is correct, because the fibers are projective spaces.
Yeah, so you just need to somehow glue them.
It's a bit, yeah, so the point is that you can do it somehow locally, so you can first do it in affine charts explicitly, more or less, and then, the tricky thing is to understand why you can actually glue them, but it's some local computation, and yes. So the idea is that you can always add to the pullback of the Keller form on M some you can add something that is positive along the fibers and small enough when you go away from the exceptional divisor. Then it will make your form positive along the fibers, and it will not spoil the positivity in the other directions. So you will get a Keller form. So okay, I don't know, maybe for the next time I'll put it into the exercises with some instructions, but okay, for now let's just believe in this. Alright, so next let me, so I wanted to talk a bit about the Keller potential. So you have seen that the Keller metric on CPN was locally exact, and actually it was a del bar of some function, and that is always the case. So the function is called the Keller potential. Let me first recall Ponca lemma and Dolbeau lemma about differential forms. So reminder. First thing is Ponca lemma. It says that closed K form is locally exact. So what it means is that if you have some open subset in Rk, for example, and you have some K form on this open subset which is closed, then any point has a smaller neighborhood. U prime, for example, such that the restriction, so there exists this neighborhood and there exists some K-1 form, K-1 form on U prime, such that the restriction of alpha to U prime is the differential of beta. And there is also a holomorphic version of this called Dolbeau lemma, which says that a del bar closed zero K form is locally and del bar exact. Del bar exact. So very similar to the previous case, only we have these forms on. So this is not K, this is N. So we have these forms on Cn, on an open subset in Cn, and I will not write down the exact statement, so it's similar. And let's now prove the proposition about the existence of the Keller potential for a Keller metric. if we have a scalar form on M, and then for any point there is some neighborhood of X open, and a function which is a C infinity function defined on this U such that omega restricted to U is imaginary unit times del bar phi, and also this function is real. Just like in the case of the projective space, when this phi was the logarithm of some sum. Proof. So let's let's apply Ponca lemma first. Ponca implies that there is U and some form, let's call it beta for example, which is a one form on U, and the restriction of omega to U is the differential of beta. So now let's decompose beta into 1, 0 and 0, 1 parts. They are complex conjugate because beta is a real form. So this Ponca lemma, well, I mean, it works for real forms. So then let's write differential of beta is, so what is it? It's del beta 1, 0 plus del bar beta 0, 1, del bar beta 1, 0 plus del beta 0, 1, and plus del bar beta 0, 1. I just decomposed both beta and the RAM differential into components. So this is of type 2, 0. So this part is of type 1, 1, and this part is of type 0, 2. On the other hand, omega is, of course, it is of type 1, 1, right? So these two pieces have to vanish. All right, so that's 0. So now we can apply the second, the Dolbeau lemma. So there exists, well, probably I have to shrink U, but I won't introduce more notations. So there is some function f on U, and then beta 0, 1 is del bar f. Actually, right, I want to, okay, so I want to write it like this. So this imaginary unit times del bar f. So I just divide f by the imaginary unit if necessary, and then I can assume that I have this. So then beta 1 0 is minus the imaginary unit del f bar. And then what do we get? So d beta is the imaginary unit times d of del bar f minus d del f bar. So what do we get here? So this is the same thing as del bar plus del bar squared, but the del bar squared is 0. And similarly here, so this is del squared plus del bar del, so this is 0, and this is a minus del bar, like this. So finally we get so I can write it like this, del bar of f plus f bar, and then I define this to be phi. And I get the claim. So it's a real function. So the Kähler metric is essentially determined by a function. So it's an envelope of a Hessian in the real case. This del bar operator is a complex Hessian, so somehow it's a matrix of second derivatives of some function, and the metric is just given by one function locally. So that's one important property of Kähler metrics that we will use a lot. All right. So are there any questions about this? Okay. So next thing I wanted to. So that's somehow the first part about Kähler metrics, and now so next thing I wanted to discuss is about connections on Hermitian bundles, because I need this later. So I haven't mentioned connections so far, but it is very important for us. So let's at least quickly recall a few things about connections on Hermitian bundles. So let me start it here. Okay, so first again we start from some complex vector bundle over M, which is a complex manifold, and a connection, I just recall the definition, a connection on E is an operator or a morphism of sheaves of C vector spaces of sheaves of C vector spaces which I will usually denote by nabla. So I view this E as a sheaf of C vector spaces, and then the morphism goes to lambda 1 m tensor E. So somehow I want to always consider today these complex valued connections, so my one forms are also complex valued, and such that it satisfies the Leibniz rule, nabla of f times s, where s is a section, f is a function, is df tensor s plus f nabla s. For any function and a section of E. Of course, we always extend, so we already had a similar thing, right? So this complex structure operator on E. The vector bundle is not holomorphic yet, so we don't have any holomorphic structure operator, but a connection is similar, but the only difference is that here we have lambda 1 and not lambda 0, 1. And then similarly as before, we extend nabla always by Leibniz rule. Which I will not write again because it's the same as before. And then also, well...
you mean extend to higher differential?
Yes, exactly. So, well, let me write it down again. So it will go from lambda k tensor E to lambda k plus 1 tensor E. And the rule is that if I have a k form tensor some section, this will be d alpha tensor s plus the sign minus 1 to the k alpha, and here I take the wedge product with nabla s. All right, so so the notation for this nabla, so I will usually write as follows. So notation: if I have a tangent vector, then I can take this one form and substitute this tangent vector into the result of somehow the action of nabla. So then I will write it like this. So this is nabla us. So this is u convolution with nabla s, where I mean that I just take nabla s and then I substitute my vector field into this one form. So that's as usual. And okay, now so we have also the decomposition of lambda 1 m into two types. So we decompose a nabla into nabla 1 0 and nabla 0 1. They are so the corresponding well, that's just the composition of nabla and the projection to the corresponding 1 0 0 1 component. So here I have E maps to lambda 1 0 m tensor E, and the other is similar. So let's recall that if we have two connections on E, then the difference is already C infinity linear. It is linear over this structure sheaf of C infinity functions. Because if we take a difference of two connections, then this term, these two terms, somehow they are the same for the two connections, and if we take the difference, then they cancel each other. And the conclusion is that if nabla and nabla prime are connections on E, then the difference is a global section of the sheaf, of which sheaf? So it's a morphism of vector bundles from E to lambda 1 tensor E, or you may say that it's just a one form with values in the endomorphisms of E. That's the same thing. Vice versa. So I can take any such endomorphism value at one form and add it to my nabla and get some other connection. So in particular, if I start from a trivial bundle, for example, if I restrict everything to some open subset in M, where the bundle E trivializes, then I have one obvious connection on this trivial vector bundle, which is just the Dirac differential applied to the coordinates. So if E restricted to U is trivial, so this is just C R vector space, well, tensor product with the sheaf of C infinity functions, well then the D is a connection here. So, well, by D here I mean just the differential applied to each of the coordinates. So here a section is given by R coordinates, S1 and so on, SR. And then D of this thing is just the collection of R1 forms. Okay, so this D is a connection, well, because Leibniz rule is satisfied, obviously. And then the conclusion is that any connection, so if I now restrict this nabla to U, then it will differ from the differential by an endomorphism value at one form. So nabla restricted to U will be D plus A, where A is the endomorphism valued one form. Or one may think of it as a matrix consisting of one forms. So R times R matrix consisting of one forms. So that's the local expression for any connection. And now the curvature. The curvature of a connection nabla is by definition nabla squared. So what does it mean? It means that I extend this nabla to an operator and then I apply it 2 times. And then, if I do this, then I get what? I get a map from E to lambda 2 M tensor E. And this is also a C infinity M linear. morphism. So why is this? Well, that's easy to check, just because of the Leibniz rule. So let's check this quickly. So here I apply nabla. So here I get d squared f, which is 0. Then I get minus df which nabla s. And here I get, okay, so nabla f, this will be df which nabla s with a plus, with the opposite sign, and then plus f nabla squared s. So these two things cancel, and I get this identity. The local expression for curvature is that, so if I write it like this, then locally R is given by the following formula dA plus A which A. So that's a matrix of one forms, and I apply the differential to each component of this matrix, and this is just the matrix product, but when I take the product, I multiply the components, I take the exterior products of the components of these matrices. So, all right. So that's the expression for curvature. And now, so if we have a Hermitian metric, we may first before the Hermitian metric. So now let's assume now that E is a holomorphic vector bundle. In this case, we also have this del var E operator. Recall that this goes from E to lambda 0, 1 E, 0, 1 M tensor E. And that looks exactly as the 0, 1 part of nabla. So we say that nabla is compatible with the holomorphic structure if this nabla 0, 1 coincides with del bar E. So the definition is that nabla is compatible with holomorphic structure if nabla 0, 1 equals del bar E. And then a Hermitian metric. So if we have now a Hermitian metric, then nabla is compatible with this H. If we have the following, so if we take, let's take two sections of E, S and T, for example, and let's compute the differential of their product with respect to H. And then my condition is that this is the same as H of nabla S, comma T bar plus H of S, comma nabla T bar, like this. Here when I apply H to, so that is one form with values in E, so I apply this H only to the second part. So what I get is a one form as a result. And on the left hand side I also have a one form. So that's the condition, and the claim is that for any Hermitian vector bundle, there is always a unique connection which is compatible with the complex structure and the Hermitian metric. So that's a proposition. So for any Hermitian holomorphic vector bundle E, there exists a unique nabla compatible with holomorphic structure and Hermitian metric. So this connection is called the Chern connection. Nabla is called the Chern connection. Okay, so before we prove this, so let's maybe make a break now, as I promised, and then go on. So I think, well, let's, for example, resume at 7:15. 7:15. Нормально, да? 10 минут.
Да, немножко больше.
So, okay, so how to prove this? Let's find such nabla locally, and then since locally this conditions uniquely determine this nabla, so we can cover our manifold with some open subsets, and if such nabla exists and is unique on every open subset, then it will define a connection globally because of the uniqueness. So that because on the intersections of the open subsets, the restrictions of those local things will coincide because of the uniqueness. So it is enough to prove that nabla exists and is unique locally. So we trivialize E as before. And we are looking for a connection. Yeah, so since since E is holomorphic, we may actually trivialize it in such a way that the corresponding constant sections are holomorphic. So let me write it like this. So trivialize E by local holomorphic sections. S1 and so on, SR, for example. And then oh, sorry. Yeah, is it better? Yeah. Okay, so we trivialize E by local holomorphic sections, and in this case the operator del bar. So what do we have to prove once again? That this nabla is its 0,1 part is del bar, and that it is compatible with the Hermitian metric. So the del bar operator in this trivialization is given just by applying del bar coordinates. We are looking for a nabla of the form D plus A, where A is some endomorphism valued 1 form, and since nabla 0,1 should coincide with DE, we must have that nabla Si is of type 1, 0. This means that this matrix, consists of 1, 0 forms. So A is lambda 1, 0 m tensor endomorphisms of E. Right, because somehow, what does it mean if we? What does it mean that this condition, in terms of this local expression D plus A? So Si, in my trivialization, it corresponds to a constant function. Somehow the coordinates of this section are like this. So I have the unit on the position I. And then the differential of such thing is 0, and then that just means that so this is Si, so this in the coordinates it's the column of this form. Yeah? So I just multiply A by this column, and then I get the row of this matrix A, and the condition is that what I get is so I have some column of this matrix A, and the condition is that it consists of 1, 0 forms. So that's exactly what is written here. So all elements are of type 1, 0. Then the condition that the connection preserves a Hermitian matrix. So let's write it down, what it means. So for this, let's introduce the following notation. So we had this condition, the elements Hij that are H of Si, Sj bar. So let's put them into a matrix. So H is a matrix of this consisting of these elements. It is R times R matrix. And the matrix has the property that it is Hermitian by the definition of the Hermitian form. How to write down the condition that it is preserved? So let's take two sections. So S and T. S has coordinates F1, Fr. Well, let's call better let's call this F, and the second section, let's call this column vector G, G1, GR. So then H of F and G bar is the same thing as the product of F transpose times H times G bar. Right, and then we have to so our nabla has to satisfy this condition written here on the right hand side. Now let me rewrite this in terms of my local expression for nabla. So that's going to be df transpose H and G plus F transpose dH G plus F transpose H D G, and on the other hand this should by the condition that this is compatible, nabla is compatible with H, that should be the same thing as so D plus A F transposed HG plus F A transpose H and D plus A G. All right, so this should be true for any F and G. In order to satisfy this condition, so let me just write down the outcome. So if we compare what happens here, so here I have D, F, T, H, G, so it's the same as this summand. So here I would also have F, T, H, D, G, it's the same as this summand. And then I have to compare this middle term with what remains here, and that is satisfied if and only if dH is equal to A transposed times H plus H times A. So this equality, so this works for any F and G. But now, so we have these two conditions. So where is it? So that's the first condition, and that's the second condition. So if I now decompose it into the forms of two types, okay, sorry, so I have probably forgotten this complex conjugation everywhere, right? Because, yes, right. So, complex conjugation should be here. So this is a matrix of 1, 0 forms, and this is a matrix of 0, 1 forms. And on the other hand, so here, so this first summand is of type 1, 0, the second summand is of type 0, 1. So actually this will be true if and only if a t h equals del h and h a bar equals del bar h. And this is if and only if a t is del h times h minus 1 and h inverse. And the second condition is actually equivalent to the first one. So, well, first, okay, so let's apply the transposition here. So this will be h transposed inverse, but the h transposed is the same as h bar. So from this Hermitian condition, so h bar inverse and times d h bar. And the second condition is the same, because again I can take the conjugate of this thing. And yeah, so that's the same condition, obviously. So you see, my two conditions, they uniquely determine this matrix value matrix of one forms A. So from here I see that locally it always exists and it is unique, so it's just given by this expression. So this proves the proposition. And then we can look at the curvature of this connection. So the curvature is given by this expression. But so let's write this down. So this will be del bar of h bar inverse del h bar plus del h bar inverse del h bar plus h bar inverse del h bar h bar inverse del h bar. So what do I want to do here? So I want to
So may I ask the questions?
Yes.
I missed something. So we have proved that if nabla is compatible with Hermitian metric, then it is unique and defined by this formula. But does it imply that? So if nabla is defined by this formula, does it imply that it is also compatible with the holomorphic structure?
Yes, so the condition that is compatible with the holomorphic structure is this one. And it consists of 1-0 forms. So this H is a matrix of just some functions.
Right, I mean, so if we just assume that nabla is compatible just with Hermitian structure, just with Hermitian metric. So it is. It automatically implies that it is compatible with holomorphic structure.
No, it doesn't. No, because so these are just two conditions.
I missed something.
Okay, so I used both conditions when. Okay, so probably it's not to write this. So I want to write it. So this. Okay, plus. So let's call this condition star, and this condition double star. So then I claim that these two conditions, they are both equivalent to this pair of conditions.
Okay, I see.
Yeah, so same thing. So it was not written. It was not well written. So yeah, right. So that's a condition of compatibility with H, and then when we combine these two conditions, then we get this equivalence. Okay. Yeah. So more questions. All right, so I was going to now compute the curvature. So what do I get here? So if I apply this del to H bar inverse, H del H bar, so of course if I apply del to this part, then I get 0 because del squared is 0. So how to compute a differential of the inverse of a matrix is just, well, I recall this. So if you have an inverse of some matrix, well, let's call it X, so the differential is computed like this. So we have to take X times X minus 1 X inverse, so compute the differential of this expression. It will be 0, right, because X times X inverse is the identity matrix, so it's a constant. So then I have a formula like this, and this means that del of X inverse equals minus X inverse times del X times X inverse. So in this case I actually get, so what do I get? H bar inverse del H bar inverse, and that is actually, so now, yeah, so and so that's H product with del H bar, and this is the same thing, and yeah, so a minus here also. Okay, so that's the negative of the last summand, because here, so this wedge product is, of course, I can exchange the wedge product and matrix multiplication, because this matrix is consists of functions. So I can also rewrite this as H bar inverse del H bar, and then here H bar inverse, and then wedge del H bar. So these two terms, they cancel each other, and I finally get del bar H bar inverse del H bar. So that's the expression for the curvature. So let's observe the following thing. So this curvature, it is a 1-1 form, first of all. So that's clear already from this expression. And also it has the following property. So that it is stable, and it is okay, so so if I have, I wanted to say that if I have an endomorphism of some vector bundle E, with a Hermitian metric, then there is the complex conjugation or the Hermitian conjugation operation that I can apply to this endomorphism. So how does it work? It works like this. So if I have B here, so it is mapped to B star here in the following way. So first I can view my Hermitian metric as a map from E to E bar dual, and then I can, so this is given, this map is given by the Hermitian metric. Then here I can apply B bar, so how to denote this, so B bar transpose, let's call it, so the transpose of the complex conjugate operator, and then I can go back via H inverse to E. So this composition is B star, and in terms of this matrix, capital H is just given by mapping B to the product of H inverse B bar transpose times H. So then I want to state the properties of the this curvature tensor. So this will be a proposition. So if R is the curvature of the Chern connection, then the first property is that it is actually a 1-1 form. It tends the endomorphisms of E. And the second property is that this R star, which is defined in a way I have explained, so I apply this star to the endomorphism part of this tensor, and then this will be minus R. Okay, so I think that I won't show you the proof because, well, it's just a computation. So actually, so 1 is clear from the local expression, that R is del bar H bar inverse del H bar, right? Because that's exactly, so this is a form of type 1, 0, and then I apply del bar and I get the form of type 1, 1. And to prove this second part, we need to check that, well, so that's, okay, sorry, in terms of the matrix, one has to put this complex conjugation here, in fact. If you write this down carefully, then you can see this. But then you have to check that this, well, R star is, so that if you look at this expression, then you will get a minus R, and this is, so let me leave it as an exercise. Because it's just a long computation, and in the end you arrive this identity. So instead of doing this computation, let's look at one particular case when we will use it, and we will use this churn connection in the case when we have a line bundle. So particular case. So let's take a line bundle L. In this case our matrices are 1 by 1 matrices, so they are just functions. So H is locally given by a function so it's just a function from some open subset to C star, which is, well, that's usually to C star, but since it should be a Hermitian matrix, it's actually the real valued function and positive. So anyway, okay, if we have now some trivialization of this line bundle, so we look at nabla. And so there was an expression for the churn connection, so this is the churn connection. Locally it is of the form del plus A, where this A was given by the following H inverse del H. Or you may write this as D plus del, the logarithm of H. And then the curvature of this nabla is just del bar del log H. So you see that this curvature, it's again a closed. So now the curvature is of course a form with values in the endomorphisms of E, but in the case of a line bundle, the endomorphisms of a line bundle is a trivial bundle. So it's just a 2 form, a 1-1 form, and it is clearly closed. So the form is closed. So it defines some cohomology class on our M. And I claim actually that this class is the first term class of my line bundle. Okay, so the proposition here is that, this is the first term class, but up to some coefficient, which is the imaginary unit divided by 2 pi. By C1 of L, I mean here the image of this first term class in this cohomology group. So I recall that we had the exponential exact sequence. And there was a connecting homomorphism from the Picard group of M, which is H1 of M O M star to H2 of MZ. And this was the first term class. But now from there I have a map to the real cohomology. And here, when I write this equality, I mean that the image of the first term class in the real cohomology coincides with the class of this curvature to form twisted by some coefficient. Okay, so that's right. So my idea was to show you some sketch of the proof, which is
Я чуть не понимаю сейчас, все-таки класс белизны, он почему он вещественный?
Этот не вещественный, а чисто мнимый скорее.
Да, но просто там написано, что он...
Прошу прощения, ну да. Тут надо тоже написать коэффициент, тогда будет вещественный.
Да, тогда он прямо целый, вот с таким коэффициентом прямо даже целый.
Ну, в смысле, что он область чего-то целого, да. Ну, это дифференциальная форма, как бы, дифференциальная форма дает класс в когомологии с коэффициентами в R, а не в Z.
Да, ну в том смысле, что интеграл по ней по-любому...
Ну, интеграл любому двоциклу будет целый, да. Или что то же самое, что это есть образ какого-то целочисленного класса H2M с коэффициентами в Z, при отображении H2M с коэффициентами в R. Okay, so let me try to do the sketch of the proof quickly and then we will finish here. So the proof is not very easy, so it's surprisingly tricky to prove this. Because on one hand we have the description of this line bundle in terms of one cocycle, the Czech one cocycle, and on the other hand we have this curvature form, and then we have to compare these two things. So let me first just so as the first step, let me recall how to describe C1 in terms of cocycles. So we have our line bundle, and it is given by one cocycle mu alpha beta. So these are some holomorphic functions that satisfy the cocycle condition, and we may assume, without loss of generality, that all those open sets are contractible. So that is, well, to prove this you may cover your manifold with some, well, there are maybe different ways to prove that. You can always refine your covering in such a way that all these sets will be contractible and all the pairwise intersections will be contractible. So to make the sets contractible, you can just cover, so you find a refinement of your cover by open balls. But then you may also fix some Riemannian metric on your manifold and assume that the balls are so small that they are convex also with respect to the somehow the distance function induced from the Riemannian metric. And the convexity is preserved when you take the intersections, and so all those intersections, all those balls, they will also be convex and therefore contractible. In this case, so what can we do? We write that those functions are exponentials of some also locally defined functions m alpha beta. So because those u alpha beta are so small, then this can be done. Because they are contractible, then you can always find these functions m alpha beta. And so that's one cocycle that gives me a class here in H1. And to define the two cocycle that gives me a class in H2 of n with coefficients in Z, I look at the following thing. That is n beta gamma minus n alpha gamma plus n alpha beta. And this is a two cocycle that gives me the first term class of L. So this mu, so L is given by the cocycle mu alpha beta, and C1 of L is the class of this cocycle mu alpha beta gamma. So you may check that they are integers from the cocycle condition for mu alpha beta, because on the triple intersections, so these things, so the exponential of this thing should be equal to 1 because of the cocycle condition for mu, and this means that this n, so that this expression here is an integer. Okay, and so that's the class in the second Czech homology, which is isomorphic to H2 of MZ. So we may change this cocycle mu in order to compare it with what is given by the curvature, we change it by a coboundary. So we change it in the following way. So let's say that L is locally trivialized by the sections S alpha. So S alpha is mu alpha beta times S beta. And let's define S alpha prime, which is S alpha divided by the norm of S alpha. So the norm is just this thing, the Hermitian norm. Okay, and then S alpha prime will be mu alpha beta prime times S beta prime, and the absolute value of this mu alpha beta prime will be 1. So this gives me a cocycle with values in the unit circle, actually, which defines the same complex vector bundle. So it is not a holomorphic cocycle, but the complex vector bundle is the same. And so, okay, so its first Chern class will be also the same, because this mu alpha beta differs by a coboundary. Although it's okay, so it's already not holomorphic, so this will be a coboundary with values in the C infinity structure sheaf. So then we again write down some local expression like this. So this is an exponential of 2 pi I times n alpha beta prime for some functions n alpha beta prime that are already real functions. So because this takes values on the unit circle, so because of this condition, the n alpha beta, they are real functions. Okay, so on the other hand, so what do we know about our connection in the new trivialization? So our connection is given by some one form A alpha. A alpha is just a one form. Complex valued one form. And the curvature of nabla is dA alpha plus A alpha wedge A alpha. But this wedge product is zero because it's a one form. It's not a matrix of one forms now, it's just a one form. So this is just the differential of this one form. So now well, okay, so check as an exercise that in the other trivialization, so these two one forms are related by the following expression. And then from here we deduce that, okay, so using those using this expression for mu alpha beta prime, we get that this is just 2 pi I times dn alpha beta prime. Okay. So now, so that's the relation between this co-cycle and the connection one forms. So now, how to describe the cohomology class of this the imaginary unit divided by 2 pi of R nabla. So that's a class in de Rham cohomology. So we have the de Rham resolution, de Rham complex of the constant sheaf R. So this constant sheaf has the following resolution. So these are just functions, and these are one forms. That's the de Rham differential, lambda 2m, and so on. So these are just real valued functions. Real valued. So let's define two sheaves. So one of them will be, so I1 is the image of this morphism. or that is the same as the kernel of the next differential, right? Because of Ponca lemma. So this is Ponca lemma. Because every closed form is locally exact, right? So on the level of sheaves, the image of this differential and the kernel of the next one, they coincide. And I2 is similarly the image of the differential going from lambda 1 to lambda 2. So then we have the following triples, exact triples. R goes to lambda 0, M goes to I1, and the second one, I1 goes to lambda 1, M goes to I2. Okay, so how to get from a two-form, closed two-form to the cohomology class with values in R. So a closed two-form gives me a section of this I2. So a closed two-form gives me a section of I2, because I2, just by definition, it consists of locally closed forms, and a globally closed form is locally closed, so I get a global section of this thing. So from there, by a connecting homomorphism, I go to H1 of M with coefficients in I1. So that's okay. So that's the So I first use the exact non-exact sequence for the second exact triple, and then I take this H1 with values in I1 and apply once again the connecting homomorphism, and I go to H2 of M R. Okay, so now let's apply this procedure to our curvature tensor. So how to apply this to the curvature tensor? So, well, curvature tensor twisted by this imaginary unit over 2 pi. So let's call these two maps. So this is star and this is double star. So I recall that my curvature is locally given by the differential of A alpha. So this is locally the differential of A alpha. Okay, so how do we describe this connecting homomorphisms in terms of when we work with these Czech cocycles? So we need to, okay, so we have some global section here. We know that locally this global section is a section of this sheaf. So that's exactly this A alphas. So that is locally some locally defined section of this lambda 1m, and then we take the pairwise differences and get a one cocycle with values in this sheaf. So its image under this map star here, so this map star here is given by the cocycle, so one cocycle of the following form. So there should be some minus here. So I'm sorry, but there is some convention with signs, and it is correct to put a minus here. So then if we look at this expression, then this is the same as dn alpha beta prime. Oops. Okay, so this is now a one cocycle which gives me a homology class in H1 of I1. And again, it is locally the differential of some function which is n alpha beta prime in this case. Yeah. So again, so to get its image under this double star, so its image under the double star is given by, well, again, similarly, so this will be the cocycle of this form mu alpha beta gamma, which is n prime beta gamma minus n prime alpha gamma plus n prime alpha beta. Okay, so that's exactly of the same form we started with. So we had already a similar cocycle, and the classes of these two cocycle in homologies are the same, because if you remember when we introduced this cocycle mu prime, then we changed mu by a co-boundary. So these cocycles also differ by a co-boundary. And so their classes in the cohomology coincide. So because mu alpha beta differs from mu alpha beta prime by a co-boundary. Okay, so are there any questions?
Yeah, so is there any way to prove the same statement by just looking at canonical, well, O of -1 on CPN? Because maybe I think it is more or less can be done in the case of CPN and O of -1. Just
so to prove that, yeah, okay, yeah, so that's, in this case it's easy because you can just write down a Hermitian metric on O of 1.
I mean, exactly. So I mean, the proposition is more or less clear in the case of
CPN, yes, that's right.
O of -1.
Yes.
But yeah, but we know that well, continuously line bundles is pullbacks of O of -1 or O of 1.
Okay, so you want to use CPN as a classifying space,
yes,
and say that a line bundle is the pullback? Yeah, right. So I guess the problem here will, I mean, the obvious problem is that your metric is not the pullback of the metric on on O of 1 on CPN, because we started with arbitrary Hermitian metric. And so so the strong connection is not really.
Yeah, but
and also,
well,
yeah,
I think it is more or less easy to prove that our class does not depend on Hermitian metric.
Yeah, that's also true, right? So probably yes, probably that would give you a different way of proving this, right? Yes. Yeah. So yeah, I think you're right. So that's one way.
And this is just less computational.
Yeah, maybe that's a bit. Okay, more questions.